record button. There we go. Yeah, Evan, do you remember what date the drop deadline is? So usually we try and get the test results, the test marked within a week of the test, right? So yeah, we should then, right? Like the test is on the 4th. So it should be done, 11, 12, 13, somewhere in there. So almost certainly the test 4 results will be out before the drop deadline there. Yeah, I think that's a fairly certain thing. Yeah, no problem. Good taste in restaurants on campus? Yeah, I don't think there's much. I personally don't hate the blind duck, but I mean, I did grad school at St. George, and the restaurant choice in St. George is like a totally different piece because there's just nothing around UTM, right? Like
just
UTM,
the food trucks alone around like downtown.
Yeah, exactly. Like the blue food truck, the brown food truck. That's how we refer to food trucks, by their color, right? But yeah, the food trucks. Then there's Kensington right there, right, which has all sorts of like cool fusion stuff. And yeah, I mean, at UTM, what do you got? You got a couple of big chains, right? Can students go to the faculty club? Aziz, do you know? Can you guys go to the faculty club?
I don't think so. I think I can because I became faculty at the end, but I don't think the students can.
Okay. So, because yeah, otherwise, what do you got? You got like a bunch of chains and stuff, Starbucks, Tim's, Subway, all that stuff. And then you have the Blind Duck. And then there's that little strip mall that's like a 10, 15-minute walk from campus. I don't really know what's there though.
South Common. There's a few things there. Yeah.
That's more like sit-down-y stuff though, I think, right? Like
it's not the best. Like on campus, there's a few options there or whatever.
Yeah, if you guys check the important dates, it'll tell you in there when the last date to drop a course for without academic penalty. And it's a little bit different than the age courses, right? Just because year-long courses are obviously a bit different. If you want to define the derivative function, can we directly use x without any description? Yeah, I would say that once. So this week, for example, we're talking about like power rules, product rules, quotient rules, and all that. Once we have them, you don't have to state them. I would say you're okay to use those without statement, okay? There might be a couple of occasions when you explicitly want to state it, just depending on again, remember your goal is to be as clear as possible, right? So if you think it's obvious what rule you used, then you can just use it. If you think there's any chance of ambiguity where your marker might need to, maybe isn't certain what you did, then just write it down. So a little bit it's up to you, but for the most part, when you're doing a calculation, we usually know what you were trying to do, right? As well, let's make a note for this question that's on the screen right now. I think a lot of, a good number of you have taken calculus before, and so the chain rule, but the chain rule is technically next week. So I actually want you to try and do this question without the chain rule. And if you know the chain rule, then you can use that to check your answer. But how would you do this if I didn't give you the chain rule, right? How would you figure that out? So that's a nice problem to think about, because maybe I'll give you something where a rule does exist, but you don't know it. Oh, wow, we've actually already got 75%. So that's pretty good. So I'm going to lock this down in about 20 seconds here. Though, yeah, well, we'll see. Okay. So the class answered with A being the majority answer and then D being the follow-up. The correct answer is not A. Okay, so people might have jumped to that conclusion a little bit too quickly. We have to be a little bit more careful than that, right? So let's go through this and see what we would have done. Okay, and so the important thing to keep in mind is how do we actually differentiate this thing? Because we know how to differentiate x squared, right? But this isn't x squared, this is f of x squared. So our function here, did I give it a name? No, I didn't. So let's say maybe note that f of x squared, what does that actually mean? That's f of x times f of x, right? That's what it means to have f of x squared. And I'm not 100% certain what you're saying there. Like, oh, yeah, exactly. Yeah, it doesn't have the derivative of the inside, exactly. Yeah, you're kind of chain ruling it though, but yeah. Okay, so what we recognize is that f of x squared here is the same thing as f of x times f of x. And because it's f of x times f of x, we can actually use the product rule to differentiate this, right? And so the product rule, here, I'm going to write it like this. So we've got f of x times f of x. So I'm going to do derivative of the first thing. Now I'm going to write this out a little bit longer than you have to, again, just to try and emphasize, how these things work. So you don't have to do this much work. You can kind of just go straight to the answer if you want. Right? But the product rule says derivative of the first function times the second plus the first function times the derivative of the second, right? That's how the product rule goes. And we can differentiate those things. And if we do, we get f prime of x, f of x plus f of x, f prime of x. And those are the same thing, right? Like it doesn't matter which function is on the left and right, right? The order of multiplication doesn't matter. So those are the same thing. And when you put them all together like that, you get 2 f of x, f prime of x, like that, okay? And that was D. So you have to be a little bit careful about that, right? Just make sure that like for example, if I had said to do something like, what if I'd said compute the derivative of 2x plus 1 squared, right? You wouldn't just say it's 2 times 2x plus 1, right? That's not how it's going to work out. You would actually probably expand this out, right? Or you'd write this as like 2 times 2x plus 1. And you could do it this way if you wanted to. Or you could actually expand out the exponent, right? Actually expand it out and do it that way. So if you did it that way, what would it be? It would be, 4x squared plus 4x plus 1. Any of these work. So if you want to use the product rule, if you want to expand it out, you could do it for this particular function. They all will give you the same answer. But no matter how you do it, you won't get 2 times 2x plus 1, right? Why is it ddx plus ddx? Okay, sure. So the product rule, right? Remember, what does the product rule do? So it says, if you differentiate f of x times g of x, this is just what the rule is, right? I could prove the rule for you, but we don't do proofs in this class. Right, that's the product rule. And I'm using that rule, but in this case, g and f are both the same function, right? So instead of having 2 different functions here, I just use the same function. So I'm just using exactly that rule in this line right here. Okay, everyone okay with that? Any questions? That's good. Okay, let's try and do something maybe a little bit more abstract. I mean, that was pretty abstract too, but let's do another one here. Let's try this one. Okay, now there's a couple of ways that you could write the final answer for this. So obviously part of the problem is you're gonna have to figure out which one we do. Namir, yeah, absolutely. You can do that if you want. Yeah, that is a perfectly valid way of writing it down. It depends, Connie. So there's a couple of ways you could do this, and they'll all give you the right answer. But you don't have to do it in that order. What is it? So there isn't a rule itself, but the quotient rule does have a squaring of the denominator show up. So yeah, the quotient rule does have the denominator squared in it. But there's more to it than that, right? Yeah, good, good, good. Yeah, right. We have to be careful about the signs. Signs for sure. Okay, Brandon, there is that answer that you just described to me is on the page as well. In just written in a slightly different way, but it is also on the page. It is one of those options.
Mm-hmm.
Yeah. Well, it doesn't have to, like, I don't have to give them a common denominator if I don't want to. If I did, I could, Connie. Mm-hmm, mm-hmm. All right, let's do 15 more seconds. No, sorry, 30 seconds. 30 seconds. 15 is very short warning. All right, 5 seconds. Doo-doo. Oh, it's close. All right, so it looks like B edged out A just by a single vote. B is the correct answer. A is really, really close, but as a couple of people have pointed out, so actually the difference between A and B are exactly the same answer. The only difference is that in B, this plus sign right here is actually a minus sign, right? So if you took B and you gave them a common denominator, you would actually get the answer A, except that this plus sign would be a minus sign. So that probably threw some people off, but indeed the correct answer is going to be B. So let's see how. And as I was discussing, there is actually a bunch of different ways that you could do this, and they all end up being correct, right? That's, again, sort of one of the great things about these rules is it doesn't matter what collection of rules you use, as long as you're using them correctly, you'll always get the right answer. So we want to compute the derivative of f of x, g of x over h of x, okay? So the first thing that I'm going to do is I'm going to use the quotient rule, and I'm going to treat the entire numerator as a single function, right? So the quotient rule, remember, is the derivative of the top times the bottom minus the derivative of the bottom times the top, all divided by the bottom squared. So again, you don't have to do this level of detail, but I'm going to do it just so we can really keep track of what's happening. So that's the derivative of the top times the bottom minus, right, the derivative of the bottom times the top. I'm just going to write that like this. Right, all divided by the bottom squared. Okay, so now the numerator is not too bad. This term right here on the right-hand side, that's just h prime of x, right? So there's nothing that we have to do there. The interesting thing, the thing that we have to expand out now is this term right here, right? And we're going to have to use the product rule in order to be able to do that. So if we expand that out, using what we had before, right? It's the derivative of the first times the second plus the derivative of the second times the first. Don't forget to multiply that whole thing by h. That would be a mistake that we would kind of typically see. Times h prime of x, all divided by the bottom squared. And if we expand out that top, we get this thing. Right, which again looks like A, except that there's this, you know, A has a plus sign there, and this needs to have a minus sign. But the thing is, turns out that this is actually equal to B, because with B, if you basically kind of make a cut here and write this as f prime, let me be a little bit lazy here and not include the of x's, because that's just, you know, it's a lot of writing for no reason. Okay, so the great thing here is basically we can cancel out some of these h's, right? And if we do that, we get f prime g plus fg prime all over h minus fg h prime all over h squared, and that is b, like that. Okay. And there's a bunch of other ways that you could have done this. So you could have done this as the derivative. You could think of this as f of x, g of x as one function. And then instead of dividing by h, you could multiply by 1 over h and think about it like that. Okay. You could have done this as the derivative of f of x over h of x times the second function g. Right? You could have done this as, and you know, try one of these. Don't do them all, but you can try one or two of them and just see if you get the right answer. Times f of x. You actually also could have done this as a three function product rule, right? So f of x times g of x times 1 over h of x. And all of these will give you the same answer, right? Okay, so I was asked, can I explain the second step again? Sure. So how did that turn from addition to subtraction in the last part? Oh, yeah, sorry. That should be subtraction. Thank you very much. That should be subtraction. Okay, so the second step, like, so this direct messenger, this is the step. Okay, so the only thing that I'm doing in this step is expanding out this yellow bit here. Okay, so this yellow thing is this, right? That's the derivative of f times g, me actually using the product rule there. And that's all I did was plug, like evaluate that in. The rest of the equation is the same. And then, you know, I expanded out after that and did some simplifications. This does, so I was asked a question, what is the name of this rule? This doesn't have a name, but I use both the product rule and the quotient rule. So the point is, instead of having a bunch of rules, what you want to do is you just want the minimum number of rules that you need so that all other functions can be differentiated as a combination of those rules, right? So we've got the power rule, product rule, quotient rule, and next week we'll see the chain rule. And those four by themselves are basically enough to differentiate everything. So we could make this thing up and we could give this thing a name if we really wanted to, right? But at the end of the day, it's just me applying multiple rules. So that one's a little bit easier. Okay, yeah, I had a direct question saying, can you show how I do the f times g times 1 over h? So this one. So when you do the product rule of three functions, actually, did I do this in the video? I don't remember. I feel like I did, but does anyone remember? So what you do, again, let me just maybe use a shorthand here instead. So instead of writing the of x's, maybe let me just write this. So if you have three functions, so I'm not doing the 1 over h, okay? I'm just showing you how the product rule works. You just kind of walk through And each step, you put the derivative on the next function, right? So in the first thing, I put the derivative on the first function. In the second thing, I put the derivative on the second function. In the third thing, I put the derivative on the third function. And you do that until every function has a derivative on it, right? So that's how you do 3 or more products. And so if we had f times g times 1 over h, I would do the same thing. So I would do f prime times g times 1 over h plus f times g prime times 1 over h plus f times g times the derivative of 1 over h prime. And then if you use the quotient rule 1 over h prime, that's negative 1 over h squared. Or sorry, rather it's negative h prime over h squared. And now that doesn't look like any of the answers, but it does turn out that it is actually B if you start to give things common denominators. All right, so that's how you would do that last one. So in some sense, it's actually sort of the fastest way of doing it. It's just that making it look like any of the options is actually a little bit of work. Yeah. Okay. Right on. Here, okay, what are we doing next? This is a real function. I'm gonna let you guys practice this one on your own. If you, like, we're not gonna do this one. If you want practice differentiating real functions like that aren't kind of abstract, you can basically just put them together in whatever way you want, try it, and then plug your answer into Wolfram Alpha, and Wolfram Alpha will give you the right answer, and you can check your answer from there. You can imagine we probably won't ask you too many questions like this, given that Wolfram Alpha will give you the answer. So let's probably focus on some of the more abstract things that you can't just plug into a computer, right? I think that's probably the goal. So here's a great question. This is very similar to something that has been asked on a term test before. Usually, previously in term tests, we kind of like gave a table and then made students do multiple sorts of these questions. But you can see here, this is the sort of thing, you know, you can't just plug into Wolfram Alpha. It won't help you at all. So you kind of have to still do it. Yeah, except again, the test, you know, when we gave something similar to this on a test, there was probably 4 or 5 of these, and it gave you again, a table. So it's a G has these values at these points. And yeah, it was definitely something similar to this last year. I think we might have had chain rule at that point too. So there were a couple of like function compositions that you had to do as well, but it was the same idea, right? Like it's not that much more difficult. The chain rule, I don't think is worse than the product or quotient rule. So yeah, it was very similar difficulty level, but except of course it obviously wasn't multiple choice, right? Yes, Connie, it is. Though I don't know what the 6 to 8 comment is. Jeremiah, no. No. Close though. That's sort of like the natural distractor. Sylvia, yeah. Yeah, the class is doing quite well on this one, actually. I think most people are getting the right answer, which is great. Like, I love to see that. That's phenomenal. And I think, like, again, one of these is a natural distractor. Like, we create our distractors, right? Distractors are the wrong answers. We usually create them on the mistakes that we know students will make. So if you didn't get the right answer, that's totally okay. We deliberately made them in a way that we think people will kind of make mistakes on. I'm going to wrap this up in 30 seconds here. So let's see if you can get your answers in. All righty. So let's take a look at this. All right. Yeah, 71% of the class said that the answer was B. B is the correct answer, right? So very nice. Let's go through this and see why. Chances are, if you didn't get B, you probably just made a small little mistake somewhere, and that's okay. We're going to figure that out and see if we can fix it. So to recall, we're told that h of x is x cubed g of x, right? And then we're told that g of 2 is 1/2 and g prime of 2 is equal to -1, right? So what is h prime of 2? Okay, so when we differentiate h, okay, and again, I'm going to do this in just way more detail than we want. So I see this and I'm looking, that's a product of functions, right? So I'm going to use the product rule. So it's going to be the derivative of the first function times the second plus the derivative of the second function times the first, like so, right? Now, the derivative of x cubed is what? We know this from the power rule. What's the derivative of x cubed? This is like the most concrete function we've had so far today. 3x squared, perfect. All right, so we get 3, nice, very good. 3x squared g of x plus x cubed. And then this is just g prime, right? That's, there's not much more that we can do than that. All right, so this is h prime, right? This is h prime of x. So it asks us for a particular value. So let's plug in now x is equal to 2. H prime of 2 is 3 times 2 squared times g of 2 plus 2 cubed times g prime of 2, right? And we know what g of 2 is. This thing here, right, that's equal to 1/2. And g prime of 2, that's -1. So we plug everything in, we're going to get what? 3 times 4 times 1/2 plus 8 times -1. So that's going to be 12 times 1/2. So that's 6 minus 8. So that's -2. Does that make sense? Any questions about that? Everyone's good? Hopefully that one's not too bad. I want to do another one like that. So for those of you who didn't get this one right, let's do another one like it. And, hopefully you'll get this one right. Next one is very similar. So we might not, I might not give you as much time, but let's see. There we go. So very similar. Okay, 30 seconds. Alrighty. So yeah, very good class. Again, this time, interestingly though, not in the same numbers, but the majority of the class got B, and B again is the correct answer. A lot of B's today, but yeah, B is correct. This is one that is actually way easier with the product rule than with the quotient rule. Like we'll do the quotient. I suspect most people did the quotient rule, right? Did anyone product rule this? Because I think the product rule is actually even faster. All right. Okay. Yeah. So at least, okay, Jocelyn, you're, I guess, the only person in the class who did product rule. So great. And yeah, so I'll kind of do it both ways just really quickly to show you. But I do think the product rule is actually the fastest way of doing it. Okay. And so we want what is H prime negative 1, right? Okay. So we're going to do the same sort of thing. Again, I'll start with quotient rule because I think that's, you know, how most people will have done it. So we're going to have the derivative of h of x. So that's the derivative of f of x divided by x. And again, right, way more work than I would normally do. Derivative of the top times the bottom minus the derivative of the bottom times the top divided by the bottom squared. Right? That's the quotient rule. And the derivative of f of x is just f prime, right? Nothing we can do about that. And the derivative of x is equal to 1, right? So if we plug all that in, what do we get? So we're going to get x f prime of x minus f of x all over x squared, okay? Now, we didn't want h prime though, right? So that's h prime. We wanted h prime evaluated at -1. So let's plug that in. So h prime of -1. So everywhere we see an x, right, we're going to put a -1. And that's very nice, right? Our denominator is just -1 squared. So it's just 1. So it basically disappears. And f prime of -1, right? This thing here this is equal to 3. And this thing here is equal to 2. Oh, no, that's not a 2. 2. So we're going to get, so we're going to get -3 minus 2 divided by 1. Wait, why is my minus sign wrong? Derivative of the first and second, all divided by the bottom squared. Is it, oh, it's -3. Yes, obviously it is. Okay, great. So it's -3, and then so f of -1 is equal to 2. Yeah, so this becomes +3 minus 2. Right, there we go. That's 1. Thank you. Yeah, see, I also screwed up the minus sign, right? I needed Emma to bail me out there. So yeah. Okay, awesome. Yeah, I just completely missed this minus sign. And again, that's kind of like a rough place to make a mistake, right? Now, I actually think this is easier with the product rule. And with the product rule, what I'm going to do here is I'm going to do the derivative of h of x. Okay, I want to think of this instead of being a quotient. I want to think about this as f of x times 1 over x, okay? And because I know the derivative of 1 over x, that's -1 over x squared. So when I do this, right, so again, I'm going to get the derivative of the first function times the second plus f of x times the derivative of 1 over x. And so that's going to give me f prime of x divided by x minus f of x over x squared. And now when I plug in -1, right? Like I think it's just a little bit less work to actually evaluate this. So we get f prime -1 divided by -1 minus f of -1 divided by -1 squared. And what is what again? F prime -1 is -3. So I'm going to get -3 divided by -1 minus, and then f of -1 is 2 over 1. So that again gives me 3 minus 2 is equal to 1. Right? But yeah, just a mess and a myriad of signs. And you can see even I screwed up the signs at some point. So it's easy to kind of get some signs wrong and make a mistake there. But again, right, no matter how we do it, we're going to get the right answer. As long as we use the rules correctly, right? So that's kind of a great thing about calculus that way. Okay, does that make sense? Any questions about that one? Everyone's good? Okay. I don't think I want to start the next set of questions yet because they're all kind of related. So I'd kind of prefer to leave those till Thursday. So yeah, I think actually then we can just call the lecture here. And obviously we'll follow up with office hours. So we'll just go straight into office hours. But I think that's basically the last poll question. Yeah, so you all, you've got a test on Thursday, so I imagine there's a ton of questions. So start getting your questions ready. Let me duck out here for like 2 or 3 minutes. Aziz, if you can cover me for the next couple of minutes, and then I'll come back.
Yeah, I'll be here.
Okay, cool. So everyone start getting your questions ready. We're going to go straight into office hours here. Aziz is going to cover me. I'll be back in a couple of minutes. I just want to refill some stuff.
So does anyone have any questions, anything they want to discuss? It could be about anything really. If you don't have your math questions ready, it could be about commerce. Any comments about test 4? I think what do you think of the upcoming test? I actually think it's not that bad, to be honest with you. The one thing is I want to like kind of emphasize is that you guys still have portions of last semester that are on this test. So if you guys remember like the end of the probability chapter, like conditional probabilities, expected values, stuff like that, that's going to be on your test. So like a lot of people focus only on the derivatives and forget about that last part. So keep in mind that's also going to be on your test, like the things we did last semester. So focus on that too. But in general, it's not that bad. I'll tell you that much. It's not that bad. I got a few private questions. Where's the prof? The prof went to go, I think, fill up his water bottle and grab some things, and he'll be back in a minute. For the last part, why is it f prime of x over x minus f of x? Wait, which part are you talking about here? F prime of x over x minus f of x over x squared. Just try doing the product rule here when if you're doing this question again, try doing the product rule and you'll see where this came from. So the first part, he just did the differentiation of f of x, which is f prime of x, and he kept 1 over x the same. And the second case, he kept the f of x the same, and the derivative of 1 over x, which is minus 1 over x squared, and that's how they got that. Does the upper year, I got another private question saying, does upper year commerce get any easier? I think personally it gets easier after second year, mainly because then you do your very specialized courses, and usually those are the ones you pick yourself. So you tend to enjoy them a little bit more. So they get a little bit easier, but first and second year are a lot more generic. So they tend to be harder because they're not kind of specialized for you. They're more like generic for everyone. So I think third and fourth year are easier than first and second year for commerce. Is there a MAT133 tutorial at 6 tonight? Yeah, there is I got another private question saying, is there a tutorial today at 6? Yes, 6 Eastern, correct. There's a tutorial that starts in 5 minutes. I lead that one. I have a tutorial today at 6 p.m. and 7 p.m. Eastern. So you can go to any tutorial you want. You don't have to be registered for that tutorial. You can show up to whichever tutorial you want that fits your schedule, even if it's not the same one that you are registered for. Questions about will the term test have questions about combinations and permutations? Not necessarily like explicitly, like find the combination of such as such, but there is a portion about probabilities, right? Like the conditional probability section that might have something implicitly within there.
Yeah, like you've got to know what those things are, because you get asked to do probabilities on them, but it won't be explicit counting arguments, right? Like term test 3 was, count these things, right? And term test 4 could have some things where you need to do some counting for probability reasons, but it won't explicitly be, count stuff, Ariana. So hopefully that makes sense.
I have a few more private questions here. I'll go through them very quickly.
Okay.
Like one of the questions was like, how much of these math like topics do we use in upper year courses? I'd say like a lot of what we did first semester is used a little bit more than second semester. We do a bit of derivatives as well in some of the economics classes, especially econometrics. So it is used, right? Like maybe we don't go as much as in depth as we do in this math course, but we do use elements of math that we did throughout this whole year in upper year courses. So I'd say there is connections there. Yeah, and mainly in econometrics and finance courses, there's a lot of math involved as well. Like maybe not like high level math like we're doing right now, but at least elements of like the basics of everything we're doing right now. And the tutorials, I got a question. Will tutorials today be different than the tutorial Thursday? No, they're going to be the exact same. We try to make the tutorials standardized. So whether you go to the tutorials on Tuesday afternoon, Tuesday evening, or the Thursday morning or Thursday afternoon, we try to make sure that they're all pretty much the same. It's just that depending on the TA, the teaching style might be a little bit different, but the questions and the answers are the same. And then last question I have here. I guess this is the branding question. This question everyone can see here. The test information page is up right now, so you guys can go through that. But essentially, yes, the last portion of the probability chapter and the first portion of this new chapter, which is a calculus chapter. So again, just you can go through the test information page and you should be able to find quite a detailed list of what's going to be on this test.
Sure. Okay, Aziz, I imagine you got to take off. I'll take it over from here. Thank you.
Yes, I will. I think I answered all the questions anyway. So.
All right, right on. All right, see you later, Aziz. Can we discuss Bayes' theorem? Sure. Try and find me a Bayes' theorem question if you can. Yeah, chapter 6 is not in, none of the derivative stuff is covered. Precisely by limits being tested, we mean week 1 and week 2. Actually, week 3 is also covered. So the continuity, wait, is it? No, not week 3. Wait, week 3 was last week, right? We started derivatives last week. So right, week 3 is not covered. It's limits, continuities, and that sort of stuff. So continuities is in there, but but differentiation is not. That being said, you can imagine a scenario in which you're asked to compute a limit that looks like a derivative, right? Like that's totally fair game because we did learn how to do those things in weeks 1 and week 2. But no, we're not going to explicitly do test derivative stuff. The reason for that is basically I think enough of you are probably freaking out by the fact that there's expected value and probability in there in the first place. And so we didn't want to dump more on it because we already have the end of chapter 4 and chapter 5 in it. So we said, let's not worry about chapter 6. We'll worry about that in like test 5 and stuff. And so that was the idea there. Should reviewing polls be enough? Generally, no. I mean, reviewing polls, and Christian, I do see it 436. So reviewing polls is a good place to start, but the problem with polls is that they're all multiple choice, right? And obviously when you do your test, it won't be multiple choice. So at some point you should be going through, you should be doing the recommended problems as well that go with the readings and these sorts of things, right? So make sure that you take a look at that. And don't just do the poll questions, right? Poll questions, again, are supposed to be a starting point for you to jump off into some of the more complicated stuff. Writing assignment 3C, sure, I'll write that down. Okay. Yeah, and exactly. Yeah, so I wanted to give you guys lots of warning about like the conditional probability stuff. Yeah, textbook exercise is definitely a good place to work on because they tend to look a little bit more like test questions. And in fact, a lot of them are test questions, right? A lot of them are test questions from previous years. Okay, so first request was for, what was it, 436? All All right, so give me a second to see if I can't pull this up. 436. Ooh, yes, nice. Okay. Okay, chapter 4, 27, 29. Right. Okay. Yeah. Well, hopefully you find time though to practice, because yeah, obviously practice is going to make a big difference. Okay. So for this question, DN means dice to end sides. Yep. Consecutively numbered. D4. You're given a bag consisting of a D4, 3D6, and 1D20. You reach in the bag, you draw a dice at random, then roll the dice and record the number of results. So that the probability you get is the probable dice fair is the expected value of your roll. Okay. So 436 is an expected value problem, right? We have all these different sided die. And in our die, we've got a D4, we've got a bunch of D6s, and a D20, right? So maybe just let me indicate them by that. Probability of picking any of them is the same, and then we roll it, and we're trying to figure out what the probability of our expected outcome is. So we have a random variable, which is just the thing that's shown on the die, but this one's going to be a little bit messy to actually do. So let me see if I can think of an easier way of doing this. This kind of uses linearity of expectation, which we don't technically know about, but yeah, let me see if there's kind of a nicer way of doing this. Now I think, okay, so you guys don't know about linearity of expectation, which is the easy way of doing this. So let's do it the hard way. So what we're going to do is we're going to let the random variable X be the number shown on the die. Okay. So what's the range of X? Like, what are the possible numbers that could show up as a result of rolling one of these 4 or one of these 5 dice? No, it's okay though. Like, because I kind of want to do it with the class, and but yeah, Brandon, I'll ask you if I need anything done quickly. So, class, what is the range? Oh yeah, close. Okay, all right, very close. Yeah, this is expected value question. So exactly, it's 1 through 20, right? An area, I want to be careful. It starts at 1 because any of these dice could roll a 1, right? So 1 is actually the minimum probable thing. And now what we need to do is we need to figure out what the probability that we roll each of these numbers is, right? What a mess. So maybe I'll show you the quick way of doing this afterwards. Anyway, so now we need to do, what is the probability that X equals 1? Okay, well, all the dice can show a 1, right? So if I pick the D4, there's a 1 in 5 chance that we pick the D4. And then what's the probability that if I roll the D4 that I get a 1? One in 4, perfect. Okay, now there's a 3 in 5 chance that we choose the D6, right? So this is the D4. There's a 3 in 5 chance that we choose the D6. If I choose the D6, what's the probability that I get a 1? Right, 1 in 6. And then there's a 1 in 5 chance that we choose the D20. And you probably know what the answer is, right? What's the probability that we get a 1? It's 1 in 20, right? Okay, Brandon, what's this number? Yeah, you do. But here's the thing. This is going to be equal to, and we can save ourselves a little bit of time. Hopefully you see this is the same as 2 and 3 and 4, right? These are all the same. 5/42, cool. Right? Does it make sense? Because every single one of these dice has the number 1, 2, 3, and 4 on it. So this computation is identical for all 4 of these possibilities. Does everyone agree? Does that make sense? Like, we ran through the exact same reasoning for what is the probability that I roll a 2. The math is exactly the same because every single one of those dice has a 2. And the probability of getting that, rolling that 2 is the same. Does that make sense? Does everyone see how we can save ourselves a little bit of time there? So these are all equal to 5/42. Yeah, I'll do it. Okay, sure. Yeah. So the expected value of a random variable is the sum over all the elements in its range of that range times the probability that x is equal to that range. Right? So we know what the ranges are, but we need the probabilities of each of those events. Okay, so that's the probability of, well, R here, I mean, we haven't started doing the sum yet. Right now, we're just computing the probabilities. So we need to know the probability of every possible outcome, right? Yeah. Okay, so now let's do the probability that x is equal to 5. Okay, now the D4 can't give me 5, right? I think everyone agrees the number 5 does not appear on the D4. So it's just going to end up being the probability of 5 is equal to 3/5, which is the probability that I pick out the D6 times 1/6 plus 1/5 times 1/20, right? So this is if I pick the D6 and this is if I pick the D20. Does everyone agree? We multiply according to multiplication rule? Yeah, because it's independent. Like, yeah, we're just trying to figure out what I mean, basically, yeah, we're using the law of total probability here when we do this. Right? So this is really, when I write this, what I'm saying is this is equal to the probability that x equals 5, given that we chose the D4 times the probability of the D4, plus the probability that x equals 5, given that we chose a D6, times the probability of a D6, right? So this is the law of total probability that I'm using here. And yeah, that's how we're doing this. So Brandon, what's this number? So it's 320s plus 100. So 4/42? I hope so. Well, I'll take your word for it, 4/42. When to multiply or add in a probability question? It depends. So this is a good question. So I got a direct message saying, when do we multiply and when do we add? So we add cases, right? Anytime we break something into cases, we're going to add those cases together. We multiply when we're still in a single case. So we're in a single case, we usually multiply the probabilities, but then we add all the cases together, right? So here in this case, this is the case where we pick a D4, right? This is the case when we pick a D6. So that's how we're determining when we add and when we multiply. Okay, what other numbers are going to have the same probability? I just said, how many faces are there in total? So there's 42 faces. And then I just said, how many? Yeah, okay, you could do that. Yeah, Brandon. Yeah, that actually totally works. I think that's probably okay. Yeah, and Kelly, you're exactly right, right? 6 is going to be the same as well. And then the only thing left is the probability for x equals 7, 8. And these are all the same because there's only one way of getting these, right? And that's only if you pick the D20. So these probabilities are all the probability that x is equal, well, let's do the 7 case, given that we chose the D20 times the probability we chose the D20, which is 1 in 5 times 1 in 20. So that's 1 in 100. But why do we include the law? Oh, sorry. You're right. This should not have been the D4. Sorry, I'm being stupid. You're absolutely right. Thank you. This should have been D6 and D20. Yeah. Thank you, person. Thank you, Kelly, for pointing that out. Yeah, that should have been 6 and 20. Yeah. Okay. So Ahmed, what we're trying to do is we're trying to compute the expected value. The expected value formula is right here. Okay. So we know what the range is, right? We just said the range is all the numbers, right? That's this thing right here. That's R. But we also need to know the probability that X is any of these numbers. So we have to compute all those numbers. Actually, Brandon, I think your calculation might not be right. Because, yeah, and it's subtle why. Because I remember a student coming up with the solution last year as well, and there was a reason why it doesn't work out. Right. So hold on, let me tell you why that doesn't work. Let's think about, let's just think about what's the probability you get a 20, right? So Brandon, according to your thing, the probability that you get a 20 is just 1 in 42, right? But the only way you can get a 20, like that's treating all those numbers as being equally likely as coming up. But a 20 is less likely to come up than a 1, right? And it's not proportional to just the number of ones that appear, because there's only one way of getting the number 20 to appear, right? Maybe that's a little confusing. Let me see if I can state that in a different way. Right, but like the probability of getting a 20 is only 1 in 100, because I have to pick the D20 and then I have to roll a 20, right? Both of those things have to happen. Versus if I just take the numbers, a bunch of number 1s and a bunch of number 2s and throw them into a bag, there's only a 1 in 42 chance that I pick out the 20, right? There's a 1 in 42 chance that I do that. But that's more likely than me both choosing the D20 and rolling a 20. Does that make sense? Yeah. So yeah, I don't think it quite works out to be these. Okay. So Christian, you say you got 11 100ths. Here, let me just double check you really quickly. It's not that I don't trust you, but I just want to make sure that we get it right. So this is going to be 3/30ths, right? Or 1/10 plus 1 100th. Yeah, exactly. So 11 100ths, good. What is this one? So it's going to be 1/20th plus 3/30ths plus 1 100th. So it's going to be 11 100ths plus 5, so 16 100ths. Let's just leave it out of 100 maybe. Does that seem right? Is it 16 100ths? I think it is, right? So 464 and 2 is 64 and 2 is 86 divided by the remaining 14. So yeah, each of those is 1 in 100. Yeah, so these all add up to 1. Okay, so far so good. So now we've just computed the probability of each of these events. Now we also have to compute the expected value themselves, right? So the expected value is, okay, so what is it? So it's going to be the outcome, 1 times the probability of a 1, which we said was what, 16 100ths, plus 2 times 16 100ths, plus 3 times 16 100ths, plus 4 times 16 100ths. Okay, so that kind of takes care of those cases where those were all the same. Plus 5 times 11 100ths, plus 6 times 11 100ths. So those were the 5 and the 6. And then the last numbers are all the same as well. And there's kind of a shorthand here. Basically, what you can see is times 1 over 100. We can shorthand this a little bit by doing 16 100ths times 1 plus 2 plus 3 plus 4 plus 11 100ths, 5 plus 6 plus 1 100th, 7 plus, oh, sorry, this should be 20. 7 plus 8 plus 9 plus ... plus 20, right? Like that. And you work out whatever this number is. You plug it into your computer and you get an answer. You could, I think if you're comfortable, you could make an argument for going straight to the final answer. So I was asked, like, do we have to do all this work and go to this final answer? I would say though, this is pretty tough. And you'll want some sort of justification for why these numbers are the way they are. And I don't know how you're going to justify these numbers without doing these calculations, right? If the calculation is a little bit easier, you can kind of go straight to the final answer. Related to that, we're very generous about not having to write down the random variable. If you don't want to do that, and you can go right to the, I mean, do we have to write and fill in the summations symbol thing first? Like do this thing? Because I didn't do this, right? Like I could have actually gone through, yeah, no, I you can skip this if you want, right? Like you can see I didn't actually use it in my solution at all. Yeah, you don't have to do that. For the sum of 7 to 20, can we write that as, no, Kelly, that would be the product of 7 through 20, right? Not the sum. Right? Okay, so you guys, you work that out and you get some sort of number. It turns out there's a way easier way of doing this. Yeah, you wouldn't lose marks. But again, right, you're going for clarity. So if something in your solution isn't clear, you might want to write that down. You have to make that call on the fly. There's a much easier way of doing this, which is I know that the expected value of a D4, actually, I just know the expected value of a Dn is always n plus 1 over 2. And so by linearity of expected value, the expected value of my random variable is the probability of my D4 times its expected value, or sorry, 1/5, 3/5 times n plus 4 plus 1, 6 plus 1 over 2 plus 1/5, 20 plus 1 over 2. And that's the same answer. But this is an advanced way of doing this. You guys don't know how to do that. Yeah, it's n plus 1 over 2. This is a good thing. If any of you have, if none of you have ever done this, you should convince yourself that the expected roll of a D, and this is important. Any of you guys are playing games or gambling, you should know what the expected value of a dice roll is, right? If you roll a 6-sided dice, the average is 3.5, right? That will come out on average to be 3.5. If you roll a D4, on average, that'll be 2.5. If you roll a D20, on average, it's 10.5. So that's very important anytime you're doing any gambling, to know what the expected value of the dice is. EDN is the expected face that will show up if you roll a DN. Okay, so let me give you an example. Let's say I tell you to roll 10 D12. What is the expected number that you should get? Uh, 6.5 is for 1 D12, but what about 10 D12? No, wrong way. Don't divide by 10. 65, right? And do it. Somebody go into Google. Okay, so if you all go into Google, you can say to Google, roll 10 D12. Right? And you should get a number near 65 on average, right? So where is, we can Google this. Oh, there's so much crap on my screen. Okay, we can say roll 10 D12. Right, and it'll roll it for us. And yeah, okay, that's pretty close to 65, right? Okay, yeah, Dottie got 63. And so I seem to be coming up a little low here. For some reason, I'm always low. There we go. Now I'm a little above 65. But basically, if you just did this over and over and over again and averaged all the numbers, the averages would roll out to be 65. Okay. And you can see there's some really bad rules here, right? 2, 2, 3, 3. DN is the side of the dice. So you might have to read 436 again, but DN, so a D12 is a 12-sided dice. And so rolling 10 d12s means roll 10 dice, each of which have 12 sides. Yeah. Right. And hopefully you see this number is pretty consistently around 65. Though again, for whatever reason, Google has decided to give me really bad rules every time. So I tend to be coming up less than 65. Yeah, 65 is the expected value. Exactly. And notice, right, my rules are all very close to 65. That was a really good roll. That's rare to have a roll that good. This is a really bad roll, right? Look at all the numbers less than 6, right? There's a lot of numbers in here less than 6. Okay, and if you just did this over and over and over again, and in fact, the larger you make the number, I don't know if Google's going to let me do 100. No, it just says go away. But anyway, the more dice you roll, the more likely you are to converge to your expected value, right? So that's just, kind of a shorthand way of doing that. It makes life a little bit easier. Okay. All right, so let's see. Because the average for 1d12 was 6.5. Yeah, exactly the same. So that's what it is for 1d12. But then the question was, what happens if you roll 10 of them? And it turns out you can just multiply the answer by 10. Done. Okay, nice. Yeah. If it goes up, so on 20, you should average 130, right? So if you roll 20 d10, I bet you those numbers get much closer to 130. On the DN in general, the formula is 1 DN. Yeah, so the average roll of 1 DN is n plus 1 over 2. And you should do that calculation if you don't believe it, but that is in some sense, like, what is the average of the first n numbers? The answer is n plus 1 over 2, right? Like, what is the average of 1 plus 2 plus of 1 and 2 and 3 and 4? It's 2.5. And it's always n plus 1 over 2. And the reason why that works for dice is because dice has the numbers 1 to n, and they're all equally likely. So the expected value is just the average, right? They end up being the same thing. Okay, someone asked for 437-C. Let me actually refer you to Piazza for that. And then there were a couple questions before that that I want to take. But let me just quickly pull up the Piazza post for that, because we were doing it on Piazza. So how do I share a thing? I guess if I just do this. Oh, I see. Yeah, because we're still kind of in the middle of that conversation, right? So what I would say in the case of C, what you should do is, here, let me just put it in the Piazza right now. So in this case, assume that Mississauga and Toronto have the same number of books. So the probability that a book is sold in Mississauga or Toronto is equal. Use this to right? So you're going to do the same thing that we do here. You're going to say, what is the probability that the book you bought is from Mississauga times the probability that it's profitable, and then use that in order to figure out the profit, and do the same, exactly the same sort of thing that we did here, right? So give that a shot and see. And then Davin, if you want to contribute to there, like get an answer based off of the hints and the resolution that I've given, if you post it in there, that'd be a great contribution to this question. I think it'd be really, really good. Okay, we can talk about it a little bit more, but there are a couple more in the to-do list. Okay, so somebody asked for writing question 3C. So let me just pull it up here because I don't want to recreate the graph. No, don't make me sign in. Seriously, this has been going really slow for me lately. Okay, it worked. I didn't have to. Multi-factor authentication. Running assignment 3C. Okay, I just want the graph. That's all I'm trying to do here. Okay. Why are you over there? Okay. How long is it? Okay, I assume that's the class. All right, so, and this asks us to do what? Find the limit of, as we approach 0 of f of x, I think. Oh, what just happened? Okay, there we go. So I think the question was find the limit as x approaches 0, f of x, right? Okay, so again, we should kind of approach this from each side separately. So we do what happens as x approach, or here, let me just make it clear I'm doing cases. So case 1, what happens is x approaches 0 from the right, right? So again, we're going to do like we did before. We're going to look at the inner function. So as x approaches 0 from the right, what is f of x doing? Right, so we're coming like along this line right here. Right, yeah, it not only, yeah, it doesn't just approach to, it equals to, right? It's exactly equal to 2. So as x approaches 0 from the right, f of x is exactly equal to 2. Right, exactly. Okay, so that means that when I do the limit as x approaches 0, f of x, this inside thing is always equal to exactly 2. So I just get f of 2 out. And what's f of 2? Yep, exactly. It's 0. Very good. So this is equal to 0. Okay. Just going to mute you because I assume you didn't mean to unmute. So look at it. It's not like approaching from above, right? It's not like doing something like this where it's not equal to 2 and it's just getting close to 2, right? It is 2, right? Like the y value of everything in here is exactly equal to 2. Yeah, exactly. Yeah, horizontal. It's a straight horizontal line. Yeah. Okay. Does that make sense? Is everyone okay with that? Are we considering what happens behind the kink? So when you take a limit, you're only concerned with what happens nearby. So you can kind of ignore what's happening over here, right? Because you're taking a limit as you approach 2. So you really don't care about that stuff. And in fact, if the function looked like even like this, and then it had a straight line, you know, the answer would still just be the same. And it doesn't matter, as long as there's just a little straight portion before you actually hit 0, the answer will be the same, right? Because you only care about what's happening nearby. So same, it's like, here, let's try it. What is the y value of this point? Right, okay, what's the y value of this point? Yeah, what's the y value of this point? Right? So the function is just equal to 2, right? It's not getting closer to 2. It's not like 1.9, 1.99, 1.999, right? It's not getting close to 2. It is 2. Right? If the limit as x approaches 0 of f of x is 0, does that make it continuous? Okay, right, Ahmed. So yeah, you're 100% on the right thing, right? So yeah, so let's just do the other side. So I mean, you're getting ahead, but yeah, you're on the right track. Okay, hold on. So direct messenger, why is it wrong to think that the limit as x approaches 0 from f of x is the limit as x approaches 2 of f of x? Because the inner thing isn't approaching 2, it is 2. Right? That's the important point. The inner function is not approaching 2, it is 2. So let's try this. So let's say this number is like, let's try it. So let's say that x or here, let's compute it. So f of 0.5, or let's do f of 0.5, right? So f of 0.5 is equal to what? Right, so take a look at 0.5, come up on the graph. F of 0.5 is equal to 2, right? Does everyone agree? Right, and then if I choose a number closer to 1, I could do like 0.1. That's also f of 2, which is 0. F of 0.01 is equal to f of 2, which is equal to 0, right? Like, what is this? What are these numbers doing as x approaches 0 from the right? Well, they're all just equal to 0. Okay, yeah, that's an interesting point, talking about pushing the limit inside, because yeah, you can't do that because the function's not continuous there, right? So you have to be careful. No, f of 2 is this thing is f of 2, right? There's a hole in the function, so the actual value of f at the point 2 is where is the dot. And yeah, Emin, same answer, right? Yeah. Is it okay? Is that good? Does everyone see that? Everyone gets it now? That hole means that the function isn't defined. It's not defined here, right? That's not f of 2, but this is f of 2. Right. Yeah. So that was kind of like what we were going for, was to kind of like throw you off that way. Yeah, it's okay. It's all right. Sometimes that just happens, right? You make a little mistake. But again, better to kind of like make mistakes on relatively low stakes things than on high stake things. Okay. And so hopefully you all see it's the exact same story from the left, right? So in case 2, as we approach x, or as x approaches 0 from the left, again, it's just constantly equal to -2. And -2 is also 0, right? So we get the limit as x approaches 0 from the left, f of x is equal to f of -2, which is equal to 0. So what did we find here? We found that both one-sided limits actually do exist, right? So therefore, the two-sided limit exists. Limit as x goes to 0, f of x is equal to 0. Okay? Right, yeah, exactly. If it was approaching -3 and 3, what would have been the correct answer? So if it was approaching 3, well, 3 is a weird number, maybe 2, right? Because 3 is like here, which is kind of a weird number. So like maybe if we were approaching 2, so in the limit as, let's say as x approaches 2, f of x approaches 3 from below, right? Right, and Ahmed, exactly. The limit is, this function actually is continuous, because what is f of 0? It is equal to 0. Right? So basically, if a question asks us the limit of a certain value where there is both a defined and undefined value, we look at the defined value. Emin, I'm a little confused about that statement. I'm a little bit hesitant to say yes. So if a question asks us the limit of a certain value where there's both a defined and an undefined value. Yeah, Emin, I'm not quite certain what you're saying there. I'm a little bit hesitant to answer until we clarify it. So like, do you mean the limit as x approaches 2 here? Because this is not, right? The function is defined at 2. It's just not continuous there. Well, no, in the limit, we would still use this. right? So in fact, we can do this. So here, let me maybe copy this graph. Okay, and let's say that we were asked, this time we asked to do the limit as x approached 3, or sorry, the limit as x approaches 2 f of x. Okay, so in this case, as x goes to 2, and we can actually do both sides at once for this one, f of x goes to 3 from below. So we actually ignore, right? We ignore the dot, right? Because we're doing a limit, so we ignore this. And then that means that when we do the limit as x approaches 2, f of x, that becomes the limit as x approaches 3 from the left of just f of x. So we're approaching 3 from the left. So we're doing this. This is actually continuous. That number is like what, 1.5 or something? So we would get that. Right? So it depends on what you mean about the whole. In this case, the, like, you know, this thing wasn't used at all, right? We actually did use the y value of the whole. Theodore, actually, that's a really good point. I don't think I've uploaded them yet. So yeah, I can do that tonight. Okay, so are we okay on this? Like, is everyone all right? No problem? Okay, good, cool. Okay, so I was asked for 427. Where's my thing? 420 or 420, yeah, 427, 429. Ooh, that's a really nice one. So 427, we also had a Piazza post on. Let me see if we can find it. And I think we did it pretty well. So whoever asked for 4-27, it's just reading this one. Now, in this one, the student goes straight to part B, but it's the same sort of thing. And so we spent a bit of time talking about this problem here. So maybe give that a read and let me know if that clarifies anything. For 29. Oh, I hate 29. Okay, 429. Yeah, I don't think that one has a Piazza post. So I'm not going to write this one out because it's quite wordy, everyone. So I'd pull it up and just take a look. So 4-29. So you have 2 bags. Bag 1. Actually, I feel like I did this one in an office hours already, right? Is there an answer sheet for the textbook exercises? Some of them, yeah. Or a good number of them, probably actually 3/4 of them, yeah. It's in the material section. It's in the same place where you download the PDF itself. Yeah. No, I did this one. Let me find it. Does anyone remember when I did 429? It was in office hours one day, but I don't remember exactly which class it was. It was last year. So it must have been in the last week, right? When did we do this? What week was this? This is the week 11 stuff. So let me find it, because then there's a recording of it. Let me see. You know, there are benefits to the pandemic, and one of them is precisely this this fact that I can just kind of pull up recordings. It's really, really nice. Okay, I'm looking at my December 2nd one here. Yeah, because this question is just a pain. Like it's not a lot of fun. There's just so many cases. You have to draw a big tree. If I can't find it, I'll do it again. But it's just really annoying. Okay, I don't see it in the December 2nd. Maybe I did it on the 30th. No, the 30th, it looks like I just ranted about how to study. Was it? Oh, so maybe I did a different question. Is that what you're saying? Oh, I see what you're saying. So it's similar, but it's not the same, right? Is that? Yeah. So it is basically example 4.20. I feel like I did this one though, but anyway, okay, let's do it again. Yeah, I think we did do a similar. Here, let me just set it up then. Maybe even if I don't do the whole thing, let's just make sure we're all on the same track of it. And again, maybe it's out there and I don't know where it is. So we've got two bags. So we've got bag one, right? Draw a big picture here. And like I said, it doesn't hurt to set this up, right? It's been a while since we did this. We could all use a little refresher. But go take a look at those last sets of recordings from last year. And right, exactly. And that's what Ariana is saying. So we've got two, in bag one is 5 blue and 2 red, right? So we've got 1, 2, 3, 4, 5. While I've got the blue, this has got 2 things. And then bag one has 2 red marbles. And this has got 3 red marbles, right? Okay. Then what do? We roll 2 fair die. Okay, so roll 2d6. If the sum of the die is greater than 10, so if the sum is greater than 10, did I say strictly greater than 10? Yeah, strictly choose bag one. Then bag one, else bag two. Right. Okay, now flip a fair coin. Oh my God, this is the worst. Why did I do this to myself? Now flip a fair coin. If the coin shows heads, add 1 blue marble to your bag and add, okay, so then flip a coin. Heads means we add a blue. And tails is add red. Okay, now choose a marble at random from your bag. What's the probability? It's red. So what is the probability of red? Okay, so again, we're gonna make, no, this is a pretty brutal question. This is way too much, but you know what? That doesn't mean it's not worth doing, because again, like anything, you wanna over practice, right? You wanna practice doing harder questions than what you see on the test, not just the same sorts of questions. So it doesn't hurt to do slightly harder questions every now and then. Okay, so we're gonna draw a decision tree. So we're gonna start, right? We're gonna roll 2d6, and we have to determine what the probability we choose bag one is, and what is the probability that we choose bag two, okay? Now we choose bag one if we roll greater than a 10. So, okay, Kelly, so we'll set it up. Exactly, it's 3 out of 36. Does everyone agree? Because how many ways can you, so you have to either roll an 11 or a 12, and there's only 2 ways of rolling an 11 and 1 way of rolling a 12. So there's only a 3 in 36 chance that you choose bag one, and there's a 33 in 36 chance for bag two. Is everyone okay with that? Everyone agree? Okay. All right, so now we're gonna say, what's the probability that I add a blue? What's the probability that I add a red? That's just 50-50, right? Because you flipped a fair coin. So 1/2, 1/2. Everyone agrees? All right, shouldn't be anything crazy there. Now, so let's say we're in the blue. What's the probability that we actually choose a blue? And even though we only care about red, let's just do the whole tree, okay? So I've chosen bag one. Let me maybe zoom out here. I've chosen bag one. I'm in this, okay, I'm in this top branch here. So I've added a blue marble to it. What's the probability that I chose a blue marble if I added a blue marble to it. Wouldn't we do heads for tails branched out for bags 1 and 2? Yes, yeah, sure, but it's a 50-50 chance, right? Because it's a fair coin. So yeah, this is heads, which is the same thing as add blue, and this is tails, which is the same thing as add red. Does that make sense? Same? Yeah, okay, exactly. So Brandon, it's 3 out of 4. So let's see, there would be 6 out of 8. Yeah, so 3 out of 4, right? Maybe let me write it as 6 out of 8, just so we can kind of keep track of why things are the way they are. So 6 out of 8 and 2 out of 8. So does everyone understand where those numbers came from? So look at bag 1. Bag 1 right now at the very beginning has 5 blue and 2 red, right? 5B and 2 red. But we're in this scenario. So we've added a blue marble to it. So in this scenario, there are now 6 blue and 2 red. And so the probability that I choose a blue is 6 out of 8, and the probability I choose a red is 2 out of, right? Yeah, no problem, whatever. You made a mistake, but it's okay. And then if we do the same thing down here, right, where we added a red, so we have 5 blue, 3 red. Maybe this is what you did, Simon. You just kind of like, there is a 3 out of 8 one. It's just you kind of might have written it at the wrong time. Right? So this is 5/8 and this is 3/8 right there. Does that make sense? Yeah. And so you just keep doing this, right? So now if we go down to bag 2, right, it's again 50-50 for add blue and add red. What was it originally? It was 2 blue, 3 red. So once I add a blue, it's now 3 blue, 3 red. So the probability of choosing a blue is 3/6. And you all know that's a half, but let's just leave it like that so we can see what the numbers are. If I add a red, it's 2 blue, 4 red. So blue, oh, why'd my pen die? It's been doing so well. Right, but you just keep doing this, and eventually you get your whole probability tree. And then it wants to know what the probability of red is. So you just find all the ways that you finish on a red and add them all up. Right, so, all right, hopefully that did it. So blue now only has a 2 in 6 chance. Red has a 4 in 6 chance. Okay, and let's make this really fat and maybe let's make it yellow. How's yellow show up? Oh, yellow is terrible. Let's not use yellow. Blue? How's blue show up? Oh, blue is okay. So now, right, we're asked for what is the probability of red. So we're going to try and find all the reds and follow them back to the beginning, right? Red like this, red like this, red like this. So the probability of each of these arms is the product of its probabilities, right? How come you have a branch for blue and red for each heads and tails for heads? I only put, I mean, okay, I made the whole, so Simon, I don't know if this is what you're asking. I just included the whole table, even though we only care about the red at the end, right? But like, you never know. If you're doing this on a test, maybe a future question asks you something about the blue. So it doesn't hurt to do the whole table, but maybe I misunderstood your question. Yeah. So I just, it doesn't hurt to do the whole thing. It also helps you sanity check because you know that when you add these numbers, you should get 1, right? Yeah, for sure. If you only care about red, you only have to include red. You don't have to include the blue. I just do it, for the sake of completeness to kind of show you how you would do this. Okay, so let's say we followed the top trail. So the probability of choosing a red, this red, is going to be 3/36 times 1/2 times 2/8, right? The probability of this red is 3/36 times 1/2 times 3/8. The probability of this red, 33/36 times 1/2 times 3/6, right? The probability of this red, 33/36 times 1/2 times 4, 6. And then you just add them all together. And that's your answer. Yeah, sure. Yeah, exactly. And again, it doesn't hurt. Like, I think it's relatively little, it's only a little extra work to include the blues, but just kind of gives you a safety net, right? Because if you compute the blue probability and the red probability and they don't add up, something's wrong, right? So it just kind of gives you that extra little double check to make sure it's okay. But yeah, that's how you would do this problem. All right, so it's a little bit long, it's a little bit nasty, but so I actually didn't plan on doing the whole thing, but I more or less did. Yeah, I think, yeah, exactly. That like decision tree really, really helps. It's definitely useful. Okay. Are there any other ones? I've referenced a bunch of people to piazzas and such. So please ask, check those piazzas and don't hesitate to contribute to them or add more. If anyone wants some further clarification, we still have some office hours time, so I'm happy to go over it. But hopefully, we answered some of it. If you want to write out the probability, would you just write P, R, B within bag one? Yeah, and Kelly, it gets a little bit long and nasty if you do it that way, but like, yeah, that's exactly how you would do it. For 38, I did patients in surgery, they go into that should be intensive care or rehab. With equal probabilities, but never go back to surgery. Patients in the intensive care or rehab have an even chance of staying in their intensive care. Why is care misspelled so many times in that question, and how have we never caught that? Patients in this hospital never get better. It's not a good hospital. Write down a matrix. No, that's Markov chains. Don't look at 38. That's a fun question. It's a cool question. It's it's the last section of chapter 4, which we didn't cover, right? What does it feel like to actually look at math as something that's interesting? I wish I could. Yeah, I mean, Ahmed, I'm willing to bet I could. You ever know people who do jigsaw puzzles? Like, I don't find jigsaw puzzles fun and interesting, but some people do. Right? And jigsaw puzzles just generally frustrate me and they make me upset. Yeah, sure. Or Ahmed, are you telling me there's nothing that you enjoy in life that other people hate? Right? There's got to be something, whether it's a kind of music or a particular type of food or an activity, a hobby, a sport maybe that somebody else doesn't like. I think we all enjoy something that somebody else doesn't, right? And it's the exact same way, right? Like maybe you like, a particular food, maybe you like sushi and your brother doesn't, or something like this. And it's the exact same sort of thing where you look at that person and you're like, I love sushi. Like, how could you not love it? And, it's the same sort of thing. Just different people have different tastes. And, if I were to try and describe what it looks like to look at math, so first of all, there's the corny kind of stupid. Yeah, that's true. Like, you don't have to eat sushi, right? There's a corny sort of, well, okay, here, let me give you an example. I hate stats. Okay. Like, I hate stats with a passion. I still had to take stats. Like, as a math student, I was required to do stats. As somebody who writes research papers, I have to use stats, right? Like, I can't avoid statistics, even though I hate it with a passion. Because as far as I'm concerned, stats is not math. Unfortunately, that's life. Sometimes you have to do stuff you don't like, right? What are you going to do? And there are people out there who enjoy stats. Math is, so the corny answer is, do you have to memorize that score? Yeah, I mean, to an extent, sure. Yeah, I mean, there was definitely like normalized or standard normal distribution stuff I had to remember. When you see real math, not necessarily this stuff, I don't think there's a lot of beauty in this stuff, but there's a lot of crazy stuff that happens in math that you look at and you're just like, oh man, there's no way that could be true. And then it turns out to be true. And that's really cool. Math is the only field the only field of study in the world that it's 100% absolute. You know what I mean? Where like when you do something mathematically, it's right or it's wrong. You've either proven it or you haven't proven it. There's no ambiguity. It's just boom, you're done. Which is very appealing for someone who like has a very rigid mind, like a mind that enjoys rules and playing by a certain set of rules. And then it's just constantly like problem solving and solving puzzles. And every time you solve a puzzle, you get a little rush of endorphins, right? Yeah. Yeah, sure. Yeah, Kelly. Yeah, absolutely. I mean, tell me, same, that's a different question. I'm happy to answer it, but it's a different question. But here, let me ask, let me ask you, you must, even when you answer a question that you know you have correct, it feels good, right? Like, even if you don't like math, it feels good answering a question and knowing you got it right? You get a little high from that, right? There's that little endorphin rush. I think everyone gets that to an extent, even if it's in a field, maybe especially if it's in something you don't like. Exactly. So it feels good. And there are those of us who maybe it feels more good, like, it feels good enough. And if you're good at it, it's easy to get that high more constantly. Do you know what I mean? Like when you're good at math too, you can just get that high just by solving a bunch of problems over and over again. And that kind of leads you down this addictive rabbit hole. And so there is that sort of positive feedback as well. But let me tell you, math's a bitch for that. Because when you do research mathematics, right, like my original thesis problem, took me 4 years. So I spent 4 years, it took 4 years before I got that high. But that high was a super big high because I solved the problem after 4 years. But let me tell you, it's not worth spending 4 years on something to get that like high for a little bit, right? Do you know what I mean? Like math is really nasty for that reason. So I always say you have to be a little bit of a masochist to enjoy mathematics. But no, it's enjoyable, and there's lots of really cool things that happen. I wish I could show you guys some of that stuff. It's so cool. But it's not the sort of stuff that you would need for a management program in economics or whatever. And if I were to teach you guys this stuff, I would get a lot of, well, why the hell are we learning this, right? Like we're never going to use it. There's still a chance that some of you might actually use this stuff. Not you won't use everything, and not everyone will use this stuff. But this is the stuff that economics and management has decided is useful for you and relevant and that you need to learn. So that's why you're learning it. But yeah, there's lots of really, really cool mathematics out there. And that helps, right? Like when you really actually do real math and you get to see the cool stuff, it makes a difference to how much you enjoy it, right? Oh, Kelly, I love to hear that. Yeah, 100%. Yeah, there's lots of cool things you can do if you can use math to win money from your friends, right? So in a thesis, do you solve a particular problem or come up with a new idea? See, this is a good question. So a PhD in mathematics involves the following. So a PhD in pure mathematics, which is what mine is in, it typically takes, the minimum it takes is about 5 years. Most people take 6 or 7. What the first 3 years are of your PhD, so this assumes you've already done like a 1 or 2 years master's. By the time you guys, let me start again. If you finish an undergraduate degree in mathematics at U of T and you do a specialist degree, you're like, where are you up to date wise? You're probably hanging around 1850 to 1880. Okay. So by the time you finish an undergraduate degree, you know a bit of the math up to about the late 1800s. When you finish a master's degree, you're hanging out around 1910, 1920. So the first 3 years of your PhD, and so that's a long time ago, right? If you finish a master's degree in math, you're still 100 years behind where research currently is. So you spend the first 3 years of your PhD catching up, typically, to about the 1980s, 1990s, and you get relatively modern. And somewhere in that 3-year period of you catching up, you start to ask questions, right? So you start to get comfortable with what questions have been answered, what questions are interesting, what questions are solved, what questions are open. And you find a question that you think is interesting, right? And hopefully that other people would think is interesting as well. So now you've got this question that you think is interesting and you're pretty sure hasn't been answered yet. You don't know because you haven't read all the papers yet, but you're pretty sure it hasn't been answered. And this is where your supervisor comes in, because your supervisor has read all the papers and does know whether your question has been answered. Yeah, see you, Jim. So then your supervisor says, you come to your supervisor with a question, or your supervisor might help you out to find a question, and you find a question that your supervisor thinks is relatively solvable and hasn't been solved yet. And then you just spend the next however long it takes to answer that problem. And then your thesis is you presenting the work that it takes to solve that problem. So typically a research paper that you would normally publish in a journal is effectively your thesis, but your thesis is much longer. So to get a PhD in mathematics, you have to have solved a problem that nobody else has ever solved before, which is quite tricky, right? You can imagine, and has to be substantially hard enough that people think it was worthwhile. So if you solve a really easy question, people will just throw your thesis out and your committee will say, no, you didn't do enough work. See ya, Kelly. So you have to do a question that people think is interesting enough, yeah, is like that. Yeah, there's lots of like crazy words in my PhD thesis. I was at a Christmas party with my wife, and somebody who had a PhD in biology asked me to try and describe my thesis to them. And there was just, I dumbed it down as much as I could, and it still took me half an hour. And it wasn't even close. Like I couldn't even get close to describing it to him. So you can look at my PhD thesis. It's on my website. I have it posted there. My master's thesis is there as well. So, right, yeah. The thing that I tried to answer, and the thing which I did answer, so I actually answered two questions. So my thesis is actually a culmination. And that's okay. It's okay to do a little bit of work. So my thesis was a culmination of two papers that I wrote. The first one, my friend and I, Peter Crooks, we were able to characterize the module structure of the equivariant cohomology of a stratified space taken as a module over the ring of, or the point, how do I put this? If you take the equivariant cohomology, the generalized equivariant cohomology of a single point space, that's a ring, and you can use that to induce a module structure over the arbitrary spaces. So we said, okay, if you take a look at these equivariantly stratified spaces, then we can compute the module structure, but only the module structure, unfortunately, not the algebra structure, but we can compute the module structure by basically building it up slowly by each of its stratified portions. So that was one. The second thing that I did was I proved the non-convexity, like the non-abelian image of the moment map is still convex when you intersect it with a positive Weyl chamber, which is generalizing a result by Kirwan that had been proven probably 2004. So in 2004, basically there are a bunch of convexity theorems which are super famous. Atiyah and who did Atiyah? No, Atiyah did it by himself, and then Presley and Siegel did it at the same time. So their original paper, I think, was in 84. And then Douister-Mat built off of this, I think, in 98, and was able to show, for example, that the real locus had the same image as the entire set. So it's a super non-surjective map. Super non-injective. Unfortunately, though, we know that most of these convexity results really fail as soon as you work in infinite dimensions, right? So if you're operating on an infinite dimensional, let's say Frechet manifold, the convexity results super fail. So you get super non-convex things. But if you have a very special subclass of things, so for example, you take a compact connected, simply connected Lie group and take the loop space on this, then there's a maximal torus, and then the moment map of that maximal torus is still convex. You lose the compactness though, because it's no longer bounded, but you still got convexity. My supervisor generalized the Douister-Mat version of this. So if you have an anti-symplectic involution on your manifold, which behaves well with your group action, then the moment map is still convex. So she proved that with Augustine Marais, who's currently at the University of Saskatchewan. And so what I did was prove generalized Kirwan's convexity theorem to that same class of manifolds. So you have to take now, you're not convex, but if you intersect with a positive Weyl chamber, Kirwan showed you are convex. So I proved that the non-abelian image of the moment map was convex as well, which is actually a really fairly hard result. And so those two things constituted my thesis. Yeah, I mean, like, I actually really regret there's something I was kind of more interested. It turns out I didn't realize this until later, but I really would have liked to do quantization more, I think, which is still a form of symplectic geometry. But the research I was doing had me dive way too much into functional analysis and algebraic geometry. And I am generally not a big fan of either of those two fields, but they were fields that I had to do in order to answer my thesis problem. And I really took advantage of the fact that the algebraic geometers and the symplectic geometers are both studying like the algebraic base loop group, but they're studying it from different perspectives and they're not talking to each other. So the symplectic geometers don't know that the algebraic geometers proved all these things. So a big thing of part of what I did is I took the algebraic geometric results, translated them into the symplectic geometry, and then used those in order to prove the things that I wanted to. And so my thesis probably looks more sophisticated than it really is, because a big part of it was me translating the algebraic geometric results into symplectic geometry in order to be able to use them, which again looks scarier than it is, but that's just because, again, the algebraic and symplectic geometers don't talk to each other. So yeah, that's what that was. It was a rough time though, because the only book in my field is the worst written book I've ever read in my life. And I just have such an unbridled hatred of that book. And it's the only book. It is like the book in the field. So after that, you have to do research papers. And if any of you have ever read a math research paper, which obviously you haven't, math research papers are also generally terribly written. So they're infuriating, right? Math research papers are papers that, see a Christian, that deliberately, you know how you guys get upset when I skip like any steps at all, right? Like a lot of people are like, no, sir, can you not skip the steps? Can you go back and do them, right? So math papers deliberately exclude most of the steps to make the paper seem more sophisticated than it is and to make the authors seem smarter than they are. It is this unfortunate reality that, you know, you can have a paper that is really well explained and the editors will say, well, you did such a good job of explaining it, the result looks trivial. So take some of your explanation out so that the result looks more sophisticated, right? See you, Davin. So what you end up getting is papers where most of the work has been cut out and it looks like complete and total magic, and you have to fill in all the details yourself, which is, you can imagine, a nightmare. So yeah, this is how it goes. Anyway, everyone, I've been rambling for a bit. Thank you so much for hanging out and listening to me talk about my thesis. Anyway, hopefully I answered some of your questions. Yeah, don't hesitate to, if you have any questions, throw them on Piazza, and I'll be happy to answer when I can. I heard that the author assumed that you know the knowledge. If you don't, yeah. But Ariana, like, what knowledge you have is a different story, right? So every author assumes that you know the same amount as they do, and that's never true, which makes it much, much harder. Yeah, I suppose. Yeah, that's true. It was a nightmare though, Han. I would not suggest that anyone do that ever. It was not a good time. Like, I burnt out so hard as a result of it. Dad, if you can explain my thesis to me, you can have a 1% bonus mark. How about that? If you can come back to me and say, I can explain to you what you did at this point in my thesis. I'll point to an arbitrary part of my thesis and I'll say, explain to me what I did here. And if you can do it, I'll give you the 1%. I mean, if you can do it, you should get 100%, right? Like that's how it should go. Yeah, exactly. All right, everyone. No, that was a fun talk. I actually really enjoyed that. Yeah, study hard, everyone. I will, I'll see you all on Thursday night, hopefully. Yeah, like I said, study hard because you got a test on Thursday. All right, everyone. Have a good night, and I'll see you in a couple days. Yeah, hopefully.